Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL's online certification course on structural systems in architecture. Today we are in the module 4, frame structure analysis and design, and we are in the second lecture of the module 4. In continuation, this is the 17th lecture, the intermediate beams. Indeterminate beams. So, in concept in this particular lecture, we will going to have the introduction with the indeterminate beam, and then we will do some kind of the discussion on the methods of structural analysis. The degree of indeterminacy have to be discussed, the force and the displacement method of the structural analysis will be discussed further, and we will see the two problems on the propped beam and propped cantilever beam actually, and the analysis of continuous beam. So, the learning objective of this particular lecture is we will discuss the method of structural analysis and different types of the methods, and differentiate between the force and the displacement method, and we will illustrate the continuous beam and the propped cantilever. See, the structural analysis is the one of the key stage in, if you say, or the steps of a structural engineering, because we have to first analyze a structure based on its the geometrical conditions, its material properties, and also its the external loading, and based on that we have to first find out the how much is the amount of external or internal axial load or the compression, tension, bending, etc., twisting or deflection is created at particular beam or so, or a particular structure or so. It may be a beam, it may be a slab, it may be the foundation, or it may be the column, anywhere first this particular stage has to be applicable, the analysis stage is applicable. So, for as you know, the structure is very complicated one, because you cannot have only single beam where the structure is going to support, or two columns or whatever. A building is actually supported by n number of beams, maybe the 50 to 70 beams, maybe some 100 columns or something like that. So, each will have the loading, and it will behave like a proper integral way, okay, in a proper way. So, in that particular circumstances, sometimes you have to take a linear beam and then analyze, sometimes we take a frame and then analyze. So, there are various ways to analysis, but the structural analysis you cannot avoid. The structural analysis is determine the internal behavior or this internal forces and the moments and the deformations of a particular structure. And this particular process, in this particular process, whatever we get as the output, those internal forces, internal stresses, internal moments, internal shear force, and the twisting or the deflections, rotations, everything will get as a output of this particular process of structural analysis, and we will take that to the further next stage, which is called the design, structural design, and then we finally design the structure. Okay. So, that is why this is a very key stage of the structural engineering. So, in this case, whatever method we can use in this structural analysis, there are a lot of various methods we can use in different type of structures, different methods. But anyway, those methods, whatever may be the methods, we have some of the assumptions, basic assumptions that we follow in developing those methods. The one is the material of a structure obey Hooke's law, and the displacement of a structure is very small. It is very small with compared to the dimension of the structure. The last week or the last the lecture in the deflection of beam, we solve a problem on the air conditioning duct, and in that duct if you remember, we have understood that the deflection is almost about the 1 by 240 times the span. So, the span is the 10 meter, it is almost 10 by 240 times the deflection. So, the deflection is very small compared to the dimension of the structure. The parameters of structure are not changed under the loading. So, there is no change. So, that we have to assume. There are various methods, I told you. There are some classical method. In this classical method, these are the some of the methods. This is the 3 moment method, the consistent deformation method, slope deflection method, methods of strain energy come under that. There are some methods which is having relaxation issues and some iterative calculations method. It is a cyclic kind of a calculative method, which sometimes holds good, sometimes because otherwise complicated structure cannot be solved by lot of equations or so. So, the Canis method and the moment distribution methods are those kind of method, the iterative kind of a method. There are method which is computer based method, because nowadays we can use the computer to analyze the structure. So, in the background of the computer, there are some actually methods actually recalculate or calculate this particular the behavior of the structure and these forces and those kind of the deformations. Those are called the matrix method, and the finite difference or the finite element method. And there are also some approximate methods are also there. They are very quick, but definitely it is approximate. It will give a tentative the values of the output, which is called the substitute frame method, portal method, or cantilever method. So, of course, we are not going to deal with all those kind of method in our these discussions or in this NPTEL course. There are various NPTEL course is floated by our faculty from civil engineering and for various IITs and all. So, you can, if you have further more interest, you can go through those courses, but in our from the architecture point of view, we will try to see that how the indeterminate beam can be solved, and for the purpose, and after solving, what is the tendency of the bending moment and how that can be actually conceived in case of the design. That is our approach. So, before we go to directly to the solving, again we let us see another way to differentiate the methods of the structural this thing the analysis. There are they call the force method of analysis or the displacement method of analysis. We will go to that. Before we go to that, let us discuss some kind of degree of indeterminacy. We already discussed this one in our first week lecture. The degree of indeterminacy is the number of unknown equations in a structure. You see, this is number of unknown equations or the number of reaction unknown equations. As the number of reactions or the support increases, you have lot of popping reactions. Okay. So, those equations, those are unknowns, those are redundant. So, we have to find out those unknowns, and we have to actually have some available 3 equilibrium equations, sigma f x equal to 0 or sigma f y equal to 0, summation of m equal to 0, or maybe extra 1 or 2, maybe sometimes it may be we can find out if there is internal hinge or link or whatever, but that is not going to be so common in the reinforced concrete or the steel structure of our civil engineering purpose, or maybe the architectural the building purpose. So, we have to actually bang on these 3 equilibrium equations, and number of unknowns are much more. If it is so, then this particular beam is called statically indeterminate beam. It cannot be statically it cannot be achieved by the statical the equations of equilibrium. So, the difference of these 2 number unknown versus the available equation is the degree of indeterminacy. So, if you see this particular continuous beam, this is called a continuous beam because this is this 2 spans are is continuing. So, it has 3 unknowns basically. I am assuming that all the forces are vertical or the gravity load. So, I am ignoring those the sigma the forces in the x direction. So, sigma f x equal to 0 will not come into the picture. So, only sigma f y equal to 0 and the summation of moment is equal to 0 at a certain point. So, certain structural point can be taken into account. So, unknowns are 3, there are 3 vertical reactions 1 plus 1 plus 1, 1 in A, 1 in B and 1 in C. So, 3 and equations available is 2, sigma f y equal to 0 and sigma m equal to 0. So, DOI, degree of indeterminacy, is 3 minus 2 equal to 1. For this particular beam, there are A and B ends are fixed end. Whenever it is a fixed, there are 2 more unknown come into the picture, and the fixed end, as you know, there are moments. The moments has to also unknown. How much is the moment I do not know. At least in the first figure I know that A and at B the moment is equal to 0. So, here it is 2 plus 1 plus 2 is equal to 5, and again I know only 2 equations available with me. So, degree of indeterminacy is 3. So, 3 unknowns are there. In this case, it is a kind of a one sided is fixed and another side is continuous and finally overhang kind of a scenario. So, it is 2 plus 1 plus 1 equal to 4 minus 2 is the degree of indeterminacy is 2. So, what does this degree of indeterminacy tells us? It tells us that you have to arrange, for the first case you have to arrange one equation somehow to solve the structure, because whenever you want to do it, when to solve the bending moment anything, you need to know the values of the reactions. So, without solving those reaction value, without getting those reaction value, you cannot solve the problem, the bending moment and all. Second case, you have to arrange 3 such equations, where from that actually tells by the this particular theories of different theories of the structural analysis. The third case, you have to arrange 2 more equations. Those equations are actually found out through some of the methods, and those methods are, I have told you, basically classified into the as a force method or flexibility method or stiffness method or displacement method. Now, whatever we have discussed in the some of the slides before, that there are computer method, there are some kind of approximate method, those are also can be classified under this umbrella of force and the displacement method. So, so in that the force methods are here. In that, if you see the force method is the primary unknowns are force. Force are going to be unknown. There are 2 type of mechanism created in a particular structure. Structure, if you use that structure as a elastic structure, it's look like a spring kind of a thing. So, if you put a force in a kind of elastic body, it will going to deform and it will be act as a spring. So, it is a kind of a stiffness and kind of a force. So, if you put a force P in a stiffness K, the deflection will be the P by K. So, that way we can say that either you have to if you want to find out that particular deflection, either you have to know the P and also you know the already find out P and you know the K, or you found out K or you know the P. So, either you have to find out the deflection, the stiffness or the force. So, in this case the unknowns are force, and in this method a compatibility equations is formed, and where the deflection or the displacement rotations are known to you. This solve this particular, we can solving these equations, redundant forces are made and can be calculated, and once the redundant forces are calculated, is now remaining portion of the beam can be or the structure can be evaluated by these equilibrium conditions or so. So, I will give you an example. Those are the some of the examples of the force method, that is theorem of least work, method of consistent deformation, column analogy method, 3 moment equation, unit load method, the flexibility matrix methods are under the force method, where force is unknown. So, suppose this particular structure, what is happening here? This particular structure is having 3 unknowns and 2 equations. So, we have degree of indeterminacy is 1. So, you have to find out one such equation. So, the one such equation is like that. I know this is the deflection, if the beam will going to under the load, if you just put the load, the beam will be deflect like this. So, there are unknown equations. Suppose the RC is the unknown equation, because I know only out of these 3 reactions one is the unknown. So, I assume that let us RC, the central one is the unknown reaction, and I know that over this particular place there is a displacement, the known displacement is equal to 0. Okay. So, displacement is equal to 0, that I know, and the unknown reactions RC I can find out from this particular condition that I know, and that is going to give me a extra, this is the that will give me a extra equation. Okay. So, this is going to be extra equation. Here I have 4 unknowns, 2 such this thing, 2 such 2 moments and the 2 reactions. Suppose this 2 green color, if I say this is I know, I can somehow know. So, these 2 are the, suppose I assume that these 2 are the unknowns. So, I have to arrange 2 such the displacement, known displacement criteria to find out the extra equation. So, this is going to deflect like this as I know, and its slope is 0 because I have these 2 are the fixed beam, fixed end. So, I know that at particular these 2 reactions are 0 and this displacement at B is equal to 0 and theta at B equal to 0, these 2 I know. So, these 2 will give you my these 2 unknown equation. So, by virtue of the deflection of the beam, if I know, this is something like a boundary condition what we are discussed in the last class, that because of the displacement or this kind of a thing or the deformation, if I know such displacement criteria, I can use that as an unknown as a extra equation and find out those unknowns. So, those equations are known as a compatibility equation. We will see today itself that how that can be executed. The displacement method, it is just opposite, where the displacement are actually going to be unknown and force will be known to us, just opposite. The other way, the force method, the displacement are known to us or the deflections or rotations are known to us, but the forces are not known. It is all opposite, and I have to create those kind of equations, and here this equation is called the equilibrium condition of the structure, and try to find out those kind of deflection from those equilibrium criteria, and finally I solve the structure. So, these are the some of the methods which is come under the umbrella of displacement or the stiffness method, slope deflection, moment distribution, Cannies method or stiffness matrix method. See here, I do not know the rotations of this A, C and B. So, those are unknowns. So, I need 3 such equation to find out those 3 unknowns, and I know there are 3 known force equilibrium, and this is MAC. Here the moment is equal to 0, here the moment is equal to 0. So, this BC is 0, AC means from A to C, BC means from B to C, these 2 are 0, and also I know that this CA and CB has to be 0 and opposite, otherwise the rotation, this particular C support will going to rotate, that has to be in equilibrium. So, easily I can find out by these 3 force unknown, force known, these 3 reaction unknowns. For this particular case, I know the rotations at C I do not know, rotations at B I do not know, but I know that there are 2 equilibrium equations. One is CA plus CB is equal to 0, otherwise the support C will be in problem, and at this end the B will be equal to 0, the BC, the moment at B equal to 0, but moment at A cannot be equal to 0 because it is fixed. That is, I cannot write down here the moment as B equal to 0. So, moment at B, moment at A is not equal to 0 here. So, this is the equilibrium equations, and that will be the way or approach for the finding out the deflections and everything for the displacement method. So, we will try to analyze a continuous beam first, that this is a continuous beam, 2 span continuity A, C and B. The L is this thing, the span, and it is under the UDL. So, as I know, this is the degree of indeterminacy of the beam is 1. So, I have to arrange for one equation. I have already discussed this one in the earlier case. So, I know that deflection is 0 at C if I say that RC is unknown. So, one compatibility equation I required, and I can break the beam into 2 parts such a way that I want to find out the value of RC, that is, let us RC, the reaction is unknown. So, what I did, I removed the value, I removed the support C, and I say that this twice 2L portion is simply supported, and I can find out the delta C, that mid span deflection, this one, because of the UDL. and also I can find out I can remove the load now, and I can put the unknown reactions at RC over here, and there will be a bulge out, the deflection is the now upward, and this delta C2 I can find out because of this RC, because it is a pointed load at the middle, right. And what will be the condition, and if you merge these two, your original beam comes over here, right. So, if you merge these two, original beams comes over here, and the compatibility equation will be delta C1 plus delta C2 must be equal to 0. Of course, you have to say them negative, one is positive, so one is negative, this one is downward and one is upward, so that has to be 0, or this must be equal to this, because at the finally at the point C there is no delta, delta at C is always going to be 0 because of this particular the support. So, first I found out how much is the delta C1. Please remember, this is my old value comes from the last deflection equation, deflection lecture, and I replace the L as 2L here, because now the length is twice of L, which is downward reflection delta C1, and here it is a pointed load case. Again I replace this 1 by 48 by EI, I replace this by 2L cube, the L is replaced by 2L, and this is the upward. So, this must be equal to 0. So, I can find out that RC is known to me, and as and when RC is known to me, I can find out the RA and RB, because RA plus RC plus RB equal to 2 omega into L, because omega is the total intensity and the total length is L, to 2 omega into L. So, RC is that 5 omega by 4. So, and this RA and RB has to be equal because it is symmetrical. So, I can find out how much is the RA and RB. So, if I know these three reactions, and if I know the UDL, I can easily draw the shear force diagram. So, I cannot draw the shear force diagram if I do not know the RA, RB and RC. So, first I have to crack that, and that cracking is the structural analysis methods. Different methods will give you those kind of the cracking, that how much is your RA, RB, RC and all those kind of reactions. The first determinates that the beam indeterminate, the reaction has to be known, then only you can find out the values of shear force diagram. Now, each and every bit of piece of the sections you can find out the shear force, and based on that you can design your beams also, right. So, this is the shear force diagram, and in the shear force diagram let us find out the bending moment diagram also. Now, if it is everything known to, it is nothing. Now, it is a very easily you can find out the bending moment diagram. So, at A and at B bending moment is 0, that I know because of the hinges. At C, at any distance from A, so suppose this is the distance from x distance, you can find out write this equation to find out the bending moment. So, at C the bending moment is minus W L square by 8, which I have placed over here. Now, one thing is pretty clear, the shear force is 0 here, and I found out at 0.375 L is the shear, it is continuously decreasing. So, I found that at this particular point shear force is equal to 0, and I know where shear force is equal to 0, bending moment has to be maximum over there, as we discussed in the last week lecture. So, in the bending moment lecture, so in that we can see that the bending moment will be highest at this particular 3L by 8 point. So, I put the 3L by 8 as the x in this mx equation and find out that the maximum bending moment, this value is equal to this much. So, I put it like that, and also I can also know another very interesting thing is that this particular point bending moment change its character, it is negative to positive, or at that particular point bending moment is equal to 0, that is also known as the point of contour flexure. And this is also I found out from putting the mx equal to 0 in the mx equation. In the last page I have it is there, this is the equation of the this is the equation of the mx. I put that equal to 0, I found out it is 0.75 L from the end. So, 0.25 L from over here, right. And this further discussion on this will be I will discuss in the next lecture, where we will discuss about the frames and the beams. So, for further for this particular point of time, we know that in under a particular given loading, a continuous beam can be solved like this. Of course, if it is much more spans, suppose it is, if suppose this is the span like a building, there are many series of rooms, so like that. So 1 2 3 4 5 6 under 6 spans or something like that. It is having the DOI equal to 4, degree of indeterminacy 4. So, I have to solve 4 equations for that. 4 compatibility equations I know. I know that this is the delta equal to 0 at all this point. So, I know that there are 4 compatibility equation easily I can achieve, but solving 4 equations, it is tedious. It is tedious for a human, and it is only 4 equations. You know, the buildings, large buildings, you have maybe such 12 spans, 15 spans, sometimes 20. In hostels, there are series of rooms. In hotels, series of rooms. It may be 20 such bays, 20 such spans, 20 spans of continuity, continuous beams. The 20 spans of continuous beam will have 18 such unknowns. DOI is 18. You know, there are 18 equations can be formed, but how to solve the 18 equations manually? It is impossible. So, we have taken other way, matrix method or some other method, or sometimes we go for some kind of, even 20 is too much, but if it is something like 3, 4, 5, we can sometimes we can go for moment distribution method or Canny's method. So, iterative process or so. Anyway, so those are the methods that civil engineers or structural engineers actually help us in our case to design the buildings, but this is the basic background of the analysis of the indeterminate beams. So, we will further discuss this particular the bending moment, and from that bending moment how the reinforcement and all these things are, the curvature and the bending is done in the next lecture. So, before go finish this particular lecture, I have that bending moment diagram explanation. Suppose this is the bending moment diagram what we got, and this is also, we can also draw the bending moment diagram in some different way, because I know that there are negative moment at the support, because this is, if we found at minus WL square by 8 or something. So, this is 0, this is 0. So, at the support you will get some negative moment. Negative moment is a hogging kind of moment. The tension is in the top. So, I have 0 over here, I have some value, I have again 0. At C will have some value, but that is a hogging. So, because of that I draw a negative bending moment diagram for the support moment. And now I look into the UDL. UDL gives me the positive bending moment, right? Positive bending moment, and that is the span moment, and I draw the individual span moment for each individual span, which is green because it is positive, and this is reddish because it is negative. Positive bending moment is a sagging kind of a moment, right? Sagging moment, because the tension in the bottom. Now, I superimpose those, so that what the superimposition means, this negative positive is clear out, and this particular portion will have a negative moment, and this particular end portion will have a positive moment. Now, you see this particular the bending moment diagram what we have drawn in this case. See, this particular is positive and this is negative, and this is again positive, right. So, it is also true, this is positive, this is positive, this is negative. So, further when we will do the bending moment diagram, it is better to use the superimposition kind of a diagram, and you can understand better. And these 2 points are the point of counterflexure, where this color changes, that means negative positive, there is a change, there is no bending moment at all. So, we see that in a particular beam, continuous beam, there are some negative moment at the support, and in the span there are positive moment, that is in the sagging kind of a character will be created. the superimposition of the bending moment diagram. So, without drawing the negative downward and the positive upward, we can do with this particular superimposition case, and we can understand better the which portion of the beam is green and which portion of the beam is red, or it is negative or positive, and we can do the design accordingly. So, we will further discuss on that in our next lecture, but before finishing this particular lecture, let us analyze another prop cantilever beam problem. So, it is a prop cantilever beam, it is having 1 degree of indeterminacy because it is 2 M A plus R A is 2 unknowns, and here R B is another unknown. So, 3 unknown reactions, 2 equations 1. So, 1 compatibility equations are there, and this is very simple. What I can do is that I remove the value, I remove the support. So, now I allow some deflection delta B over here because of the UDL, and I remove the UDL and put the support over here and allow an upward deflection at delta B upward at B, and now superimpose, and if you superimpose this two, it is nothing but the first beam, right. And the compatibility equation is that delta B, in that delta B there is no deflection. So, delta B 1 plus delta B 2 equal to 0 if you take the sign in into the action, otherwise you may say that delta B 1 is equal to delta B 2 from that. So, delta B 1 is this and delta B 2 is this, as I understand from the deflection of beam, because deflection of beam we have already discussed these two cases at the initial two cases. Or you can go through your the first lecture and see that, or maybe the PPT, and now these two are equating, we are equating these two. I can find out the value of RB, and this compatibility equations gives you the value of unknown reaction. Now, you can solve because RA plus RB equal to omega into L. So, RB is known to you, you can find out the RA, and now as and when you know the RA and RB, you can easily draw the shear force diagram. Before that you cannot, and as you know shear force diagram, so you can know that this particular point shear force is 0 at x equal to 3L by 8 from the end B, and that point definitely bending moment will be maximum. You can find out that one also. You can shear force 0 in this, so you can find out the maximum bending moment placing the value of x equal to that 3L by 8. There is some problem, I will check this one and I will rectify that one in my PPT. I think this is not correct, it has to be 3L by 8, this is a typing error. So, MA also I can find out from the, this I must check. Okay. And then MA at particular point A, just putting the x is equal to L, you can find out this is the minus WL square by 8, and then we can also find out the point of contour flexure, just putting this mx equal to 0 and get the value of 3L by 4. So, I took the reference of these books, and in conclusion I must say that the indeterminate structure are having excess reaction unknowns over the static equilibrium equations. Additional compatibility or the equilibrium equations is developed to solve the structure. Method of the structural analysis is broadly classified into the force and the displacement method. So, next lecture we will go to the, again we will continue this with the indeterminate beams and the frames. So, I have some homework for you. It is very simple homework, you have to sketch the shear force and the bending moment diagram profile of the beam. No values are given, just try to see and what should be the profile of the particular bending moment and the shear force diagram. Suppose you know A, RA, RB, RC and all those. So, what will be the profile? Thank you very much.